Hi everyone, Mr. Lee here, and today in this video we're going to do Newton's second law in 2D motion. So we are going to be using both the x and the y axes simultaneously. Alright, so before you start, you will need a scientific calculator. Now my computer has a scientific calculator as a program. Your laptops or your desktops also might have one. Now if you have a cell phone, oftentimes the cell phones also have a scientific calculator, and just in case you don't have any of those, you can go to Google and just type in Google scientific calculator and a scientific calculator should pop up. Now you want to make sure, that's very important, you always want to be in degree mode. Okay, oftentimes in math you will be in radian mode, but for physics we have to be in degree mode. If I go here to the Google one, when it first pops up, it should be in radian mode, so I'm just going to click the DEG for degree mode. Now I know I am in degree mode. Okay, you will need degree mode. Alright, so I'll minimize, put this over here. Alright, now in order to do Newton's second law, let's first cover the second law in the equation form. We have the summation of the forces is equal to the mass times the acceleration. Now, because we're going to be dealing with the x and the y forces, get in the habit of writing those subscripts. Okay, get in the habit of writing those subscripts. Now, what I'm going to do is I'm going to do one of those deep dive videos where we're not really necessarily finding anything. Rather, we are going to be just breaking down a situation or a problem in its entirety, so that you know, just in case you have to find anything, you have all the steps necessary to do so. Alright, so I'm just going to make up a problem here. Let's say we have a box, right? We have a box. And we'll say the box has a mass of, I'll do this over here, 2 kilograms. Okay. All right. And it is being pulled up and to the right. All right. So I'll do this right here. Right. It's being pulled up and to the right with a rope. So we can call this tension. Right. We can call this tension. And it's being pulled at, I don't know, let's say 10 newtons? Yeah, we'll say 10 newtons. 10 newtons of force. Okay, someone is pulling this box with 10 newtons of force. Alright, let's say because the surface is a little bumpy, okay, there's some friction involved. So right now the box is moving to the right, therefore the force of friction will be to the left. Okay, remember, the force of friction is always against motion. Always against motion. And we'll say the force of friction will be 2 newtons, not too much. Alright, so here we have our scenario. Now, we need to be able to come up with the free body diagram, so a little bit more. The very first force that we should always draw is the force of gravity, aka the weight, and that goes straight down. F of g is equal to m times g. Alright, so just get into the habit of writing it out like there. It's just a good mental reminder of the forces that are involved. Okay, and because it's on a surface, there is also this thing called a normal force, which is the surface force, F of n. Okay, and we don't know what that is yet. Alright, so if a problem asks you to create a free body diagram, this is what you have to create. Alright, now the next step is our way of further trying to find the answers using a free body diagram. So I want to make the distinction. If a problem asks for a free body diagram, you would submit something like this. What I'm about to show you is not considered to be a free body diagram because it contains this thing called components. All right, so I'm going to pause it right here. This is a free body diagram. I'm going to change it to something that is not a free body diagram. Now, what I mean by components is let's take a look here at T, this tension. You see how it's at an angle? Okay, so we can't work with angled forces. So instead what we do is we break apart this force into its x and y components. So what this means for us is this force is being pulled along the x-axis, okay, with a horizontal force like so. And we're going to call that T sub x. And is being pulled upwards like so. And we're going to call this T sub y. Okay, so that's T sub x, and that is T sub y. And it is being pulled at an angle we'll just call that angle theta for now. All right. Okay, so we have our quote-unquote free body diagrams with components. Now, the reason why you can't have these components in a free body diagram is because these are not real forces. There is no real force called tension in the y direction only. Okay, there's like this rope is pulling both up and to the right. So to claim that this rope is only being pulled in the up direction is not correct. All right, so we broke it down so that we can do the mathematical manipulations. All right, so you see here that I included some numbers. I'm actually going to erase those numbers for us. All right, I'm going to erase those numbers because I want to be able to solve this in variable form only, because adding the numbers in, I know we can all do that, right? So the next step that we want to do is we want to create a net force formula for the x and the y. So let's do the x1 first. I'm going to say f of x is equal to ma. At this moment, what you are going to do is you are going to identify any and all forces that are along the x-axis. Okay, the x-axis right here. So this is something that I do, so I highly suggest that you also do this. I go around the free body diagram in a clockwise fashion just so that I know I don't miss any forces, and I ask myself, is this in the x direction? So let's start here. Is this normal force in the x direction? It is not. Is this tension in the x direction? No, because it has both x and y. What about this y tension? Is that in the x direction? Nope. What about this tension in the x direction? Is that in the x direction? It is. It's even in the name. Now, because it's being to the right, being pulled to the right, we're going to make that positive. Okay, positive tx. What about this weight? Nope. That's in the y. Very good. And last, we have this force of friction, which is to the left, and so we will write that as negative f of f. All right, which is equal to the system's mass. And luckily for us, we only have one object right there, and we will arrange it like so. Okay, so this right here, boom, great place to start. But we can break this down even further. All right, so what I'm going to do is, before I continue on down here, I'm going to take this tension force and its components, and I'm going to do some mathematical things with it. Okay, so if I were to take a look at Tx, and we have a theta there, and I believe I have this as Tx, oops, excuse me, this should be just regular T, and I have Ty, like so. Okay. Now notice that I always include the vectors or the components of the forces as dotted lines. That's a mental reminder and also the proper way to show that these are components and not real forces. Real forces are always bolded in, okay, or filled in. Okay, now this is a right triangle, and we want to be able to describe this Ty. Okay, what is this Ty? So in order to do that, we use our trig functions. So this is our angle, and according to this angle, this right here is opposite. Ty is opposite to the angle. And this T right here, this is a hypotenuse. So you might be hearing a couple of very mathematical words here. So what I'm getting at is we need to use SOHCAHTOA. Okay, SOHCAHTOA, where the O in the SO means opposite, H represents hypotenuse, A represents adjacent. So if I were to take SOH, and I look here, we know we have to use the sine function. So this is the sine of the angle is equal to the opposite over the hypotenuse. Okay, we know we have to use this trig function because Ty is opposite of the angle. So we would rewrite this as the sine of theta is equal to Ty divided by T. So if I were to ask you, what is Ty? I'm going to do this in green to match it up. We're going to multiply both sides by T, and we should get Ty is equal to the hypotenuse times the sine of theta. Okay, and we can also do this for Tx. Now, if I take a look at the angle, according to the angle, this side of the triangle is adjacent to this angle. So we take a look here, and we see that the cosine trig function, cosine of theta, is equal to adjacent over the hypotenuse, okay, A divided by H. So we can rewrite this to say Tx divided by the hypotenuse, which is T. And if I were to ask you, what is Tx? You would say that Tx is equal to T cosine of theta. Now, I'm here to tell you that this process is something that we will do a lot from here on out. And this example, we use tension, but it could be for any sort of force. Okay, it just so happens to be that the forces that we need to break down was in the tension direction, but it could be like F of 1 or F2. It could be like all sorts of different things. Okay, it could even be the weight or F of G. But the important thing is you should be able to break down the forces so that you know mathematically what the forces are. Okay, and so for this scenario, and this scenario only, we see that Ty is T sine of theta, and Tx is T cosine of theta. So if I were to go back to the original equation, we see that we have Tx here. So instead of Tx, we can write T cosine of theta minus the force of friction is equal to the mass times the acceleration. Okay. Now, later down in the unit, we will actually figure out what the force of friction equation is, and so we can substitute that in. All right, so at this point, this is our basis of our mathematical equation. So if we were finding the acceleration, we would divide both sides by the mass, right? So I'll just show us that. So we get T cosine of theta minus F of F is equal to m divided by x, right? So this is our equation. So in order to find the acceleration, we want to isolate the acceleration. So we're going to divide both sides of mass so that we would get this T cosine of theta minus F of F divided by m, okay? If we wanted to find what the force of friction was, we would add or subtract T cosine of theta to both sides. You know what? Let me just do this one. So T cosine of theta minus F of F is equal to max. We want to see what the force of friction is. So I'm going to swing T cosine theta to the other side. So we get max minus T cosine theta. And we don't want that negative there. So I'm going to multiply everything by -1. So we get negative max plus T cosine theta. Okay, so you see how with this one equation, we're able to break down that one equation to find different things. So I just showed you two examples of how to find the acceleration and the force of friction based off of this scenario and this equation. All right, now we found the net force of the x direction. Let's try it for the y. So we want to start off with, let me erase this right here. We have the net force in the y is equal to may. We want to identify all of the forces in the y direction. So I'm going to start at 12 o'clock and I'm going around the circle. Okay. All right. So is normal force a y force? Yes, it is. So I'm going to add that in. Is this tension a y force? It is not. It has both x and y. What about ty? Is that a y force? Yes, it is. What about this Tx? Is that a y force? No, it is not. What about this weight, this F of G? Is that a y force? Yes, it is. It's going to be minus F of G because it is in the negative direction. What about this F of F? Is that in the y direction? It is not. Okay, and I went around the clock and I'm back to the beginning. So now I know I hit all of the forces and I didn't miss any, which is equal to may. All right, so we can break this down even more. We can say that the normal force plus Ty, and we figured out Ty over here. Ty is equal to T sine of theta minus, and we know F of G is just mass times deceleration due to gravity. Is equal to this equation here. All right, so this right here gives us the net force in the y direction for this scenario. Now, depending on the scenario, it might be different for you, but the strategy to get to this point is going to be the same. Now, I do want to point out something really cool. So normally, if we have a box just sitting on a surface, the weight and the normal force, they would equal each other normally. Okay. Now, let's say in this scenario, we have an outside force. Let's say a person is pushing down on the box. So when a person pushes down on the box, the normal force increases. Remember, the normal force is the force that the surface pushes. So the surface right here, the surface feels the weight of the box, okay? Feels the weight of the box, and it feels the additional push down onto the box. Okay, so the normal force is going to increase in that scenario because someone is pushing down hard on the box, and that therefore it increases the force on the surface. And the opposite is also true. So let's say that instead of pushing down on the box, a person slightly lifts up the box, right? Slightly lifts up the box. So because there's an outside force that's slightly lifting up the box, the surface doesn't have to push back as hard. And so in that case, the normal force would be less than the weight. Okay? Normal force would actually decrease a little bit. And we can see that here. So in this scenario, this rope is pulling on the box in the upward direction. So it's like lifting it up slightly off of the surface. So remember what I said, normally if there's no other forces except for the normal force and the weight, the two are equal. But because something is lifting up the box slightly, we can see what happens right here. So with this equation, let's see what the normal force would be. So remember what I said, normally if the box is just sitting there, the normal force is equal to the weight normally, but in this case, okay, I'm going to take t sine of theta, move it to the other side, and I'm going to get my weight and then move it to the other side. So we get may. So t sine of theta, move it to the other side, that will be minus t sine of theta. And this mg, move it to the other side, so we get plus mg. Okay, so we see here that the normal force is no longer just the weight. Okay, the normal force is no longer just the weight. It includes so many other things here that's involved. Now, in this case, we know that it's not being lifted up or down, right? The box is moving sideways, and so we can even say that the acceleration would be 0. Okay, we can even say that here, right? The acceleration is technically 0. So in that case, we can get a new equation like so. Negative t sine of theta plus mg. Okay, so this shows us that normally the normal force is equal to the weight, but in this scenario here, okay, the normal force has this tension that takes away from it. So the normal force is less than what it would normally be. All right, this is just one example. In the next video, we're going to take this example and we're going to explore it a little bit more. A couple of highlights that included at the end. Always keep in mind in what direction the object is accelerating. So for here, we knew that the object was accelerating in the x direction, so we did not make that 0. But if we take a look here, we know that the object was just moving side to side, so the acceleration in the y direction, it's not going to be accelerating up or down, so we made that 0 here. Now, that is a cool trick to know and to have in the back of pocket, because that actually clears up a lot of the mathematical things. Okay, I showed you how to break down the forces into components using your trig functions. Okay, and so whenever you solve these using numbers, make sure you have a scientific calculator around. And my final and probably my most important trick is I pointed out that I always like to start at 12 o'clock, okay, the very top force. I like to go all the way around just to make sure I don't miss a single force. In the next couple of videos, I'm going to do more examples, and I'm going to do examples with numbers. So I'll see you then. Bye-bye.